Good afternoon, everyone. This is CSE team number 2. This is the final presentation, final demo of our project on text-to-image generation in computer vision. My name is Mohammed Osama, and my colleagues are Amr, Mahmoud, Ismail, Marwan, and Omar. So today's agenda, we'll first talk about the introduction. We'll first discuss the problem definition and the main hypothesis, and then we will review the literature and the models that has been developed to solve this problem recently. And then we'll move to our own methodology as well as the experimental setup that we use to test this methodology. Finally, we are going to talk about the results we have achieved so far, and then we will conclude with the summary and the future works. So we start off by introducing the text-to-image generation problem in computer vision. So simply speaking, this problem, in this problem, we try to develop a deep generative model that takes as input the textual descriptions or captions and produces as an output real-looking images that are not like anywhere to be found. Like these images do not exist. Like ideally, it should produce any kind of image. So in order to illustrate this problem even further, I will ask the audience here today, and perhaps professors, you can help us with that. Which one of these images is real and which one is fake? What do you think? So looking into the details, you think the right one is the fake one. Actually, both of them are fake, and both of them have actually been synthesized by our model. In fact, all of the images we have shown today were actually are fake images. Like they are nowhere to be found anywhere else. They were automatically generated. And this goes to show the amount of progress that we have done in the text-to-image generation problem in producing images that look exactly, not only look exactly like the real ones, but they also, the model actually can generalize to more than one category and more than one class. So you may ask, what is the purpose of this problem, or what are some of the applications behind which we want to develop this problem? So the first one is the dataset augmentation. Basically, if you have a model that can generate images, you can generate any number of images and generate any dataset that you want for training deep neural networks and machine learning algorithms. It's also useful for video generation because, like, if you can automatically generate images, it means that in the future you can actually generate videos as well. It also has applications in computer graphics and computer games, scene understanding, and it's also useful for text-to-image understanding and general AI, general artificial intelligence. So the key problems that we tackle in the literature, or basically the gap that we are targeting, is that most of the models in the literature either produce high-quality images or produce images that reflect textual descriptions. But mostly, nobody does both. Nobody produces high-quality images, and at the same time, that reflect input textual description. So our main hypothesis is that when we adopt a style-based architecture, in addition to contrastive learning, that will actually enhance the quality of the images produced, as well as the text-to-image matching. So to summarize our main contributions, the first thing that we contribute in this research is that we produce a novel text-to-image generation network that actually exceeds the state-of-the-art algorithms in terms of generating images on the various dataset. And we actually show a 44% increase in the image quality using the contrastive learning in comparison to the baseline SSAGAN approach that we start with in our research. So now we will move to the next section, which is basically a review of the current literature and the current generative models that exist in the literature, as well as loss functions that have been introduced before. So the first one is the AttnGAN, which is basically a model also for, like this is one of the earliest model in text-to-image and generation. And there are three main takeaways from this model. The first one is that it uses multiple generators and multiple discriminators in order to make progressive growing of the generated images. The second one is that it uses word level attention in order to focus on the most important words in each input caption. And the final contribution of this paper is that it introduces the DAMSM loss, which is basically a loss function to make sure that the generated images actually reflect the input textual descriptions. Now I will hand it over to my great friend, Amr Adil, to talk about the SSAGAN.
The text-to-image generation problem is a hard problem because basically you are trying to move from the text space to the image space. And they are completely different spaces, so we need to do some kind of fusion between the text information and the image information in order to be able to generate the images that describe the text. So here comes handy the SSAGAN, which is a text-to-image generation architecture. The most important part of this architecture is this SSACN block, which is responsible mainly for this kind of fusion that we are targeting. Zooming into this block, we can see that it consists of this block consists of an upsample block, a residual connection, a mask predictor, and a batch normalization block. The two major important parts of this block is the mask predictor and the batch normalization part. The mask predictor is basically, it takes the upsampled image and predicts a mask that is responsible for predicting which part of the image needs some reinforcement with textual information to achieve more semantic consistency with the input text. More or less, it works like the attention mechanism. The batch normalization is makes use of the predicted mask and some affine transformation of the text feature vector with some upsampling in order to achieve the whole fusion of the text and image features as we need in the first place. Moving on to another type of architecture, which is the StyleGAN. StyleGAN architecture is not a text-to-image generation architecture. It's just an image generation architecture, but I'll explain why we are using this architecture within our model. This architecture, the generator of this architecture consists of two main parts. The first one is the mapping network, which is responsible for taking the noise vector and maps it to a latent space noise vector W, which will be later used to generate the styles A using some affine transformation. Then we have the synthesis network, which is responsible for generating the image and that achieves the style injection, which allows us to control the details of the images that we want to generate. This synthesis network consists of style blocks, where each style block is responsible for controlling specific level of details using what's called adaptive innocence normalization with some variation called the weight modulation. Moving on to another important aspect of any deep learning model, which is the loss function. We had to choose our loss function carefully. As I mentioned previously, we want to move from the text space to the image space. So we have to find a loss function that measures this, how close we are to this achieving this task. This is where we use the DAMSM loss. DAMSM loss is basically a text-image matching loss function. Before doing the training itself, we pre-train two neural networks, the text encoder and the image encoder with the DAMSM loss, in order to find that space that we want, where the image and image features and text features are meeting each other. We chose the bidirectional LSTM as a text encoder instead of the GPT-2 or BERT encoders because these two types of encoders have their own latent space, which is not relevant to our task, which is image generation. So if we wanted to use them, we had to train them from scratch, which will be time consuming and requires a lot of resources. So we used the bidirectional LSTM, which achieved pretty good results as will be discussed later. To calculate the loss functions, we have to calculate the similarity score between the words and the images, and as well as calculating the similarity score between the whole sentence and the image. We end up with 4 elements of the loss function, and the DAMSM loss is defined as the sum of all 4 elements, and that's how we achieve the similarity between the features of the text and the image. Now I'll leave you with Omar, who will discuss another loss function, the contrastive loss.
Okay, so now we have seen how to do text-to-image matching via the DAMSM loss, but we want more. We want to enhance the visual results and ensure that, for example, if we are given two similar text encodings, we want the images generated to be the same. Thus, we introduce an important block here, which is the contrastive learning, and we introduce two types here, which is the fake-to-fake contrastive learning and the fake-to-real contrastive learning. The contrastive learning basically tries to take similar embeddings, similar text embeddings, and minimize the distance between the generated two images from each embedding. So if they are similar, the generated images to be the same or close to each other, and if they are different, it should be contrasted. Should be contrasting to each other. And further introduce, we want the generated images to have a similar distribution to the real distribution of the images, and this we introduced the fake to real contrastive learning, which is basically does the same thing, but with the generated image encodings and the real images from the data set. And now we'll see how to complete the picture, we have we now matched the images together and the text to image, and now we want also to add the block that matches the text to text. And to do this, we introduce the recaptioning loss, and the recaptioning loss basically what it does is that it recaptions the generated images into using the same pre-trained text encoder that we trained before, and then tries to minimize the distance between the original encoding and the genetic caption. To see how all of this will work together, we have two directions to move on. The first direction is testing the style architecture, and the second direction is testing the contrastive loss. And to test the style-based approach, we will first do this. We'll first do this with the original StyleGAN architecture, and we want to make it text to image problem. We will introduce a text encoder block and to the mapping network and the DAMSM loss or any kind of text image matching to the original StyleGAN architecture explained earlier. And to move on, adding more blocks, adding attention, for example, we will introduce the style blocks to a deep attentional network like the AttnGAN, and we will do this via four things. First, we introduce the mapping network, and then the style injection and the synthesis blocks, as well as the text image matching as well. And so for now, we have tested the style blocks and how the style attention will work, and the second direction is to test the contrastive learning, and this will happen by testing the contrastive losses that we have introduced one by one, either one of them or both, on the style architecture that we introduced, this style architecture that we just introduced, or the SSAGAN architecture that Amr introduced, and the purpose of that we want to test the effect of the contrastive learning block on its own. So we are experimenting it on an already existing architecture that was working well, and we'll see later how it improves on it, and we will introduce it also in the StyleAttnGAN that we introduced to see how both of them can work. Now we will move to the experimental setup and then review the results.
Okay, so we have two main data sets. First is the CUP data set, which is an image data set of more than 13,000 images of birds belonging to 200 species. CUP has only one class of images, which made it easier for models to train and converge on, and allowed a much simpler representation and mapping space for the generator network than the much more challenging data set and much larger and more diverse data set, which is the coco data set, which has had more than 300,000 images of 80 object categories. Moving on. For our metrics, we have used the Fréchet inception distance to quantitatively measure the quality of our images. So the FID measures the Fréchet distance, which calculates the difference between the distributions of the real images and the generated images using the means and the variance of the two distributions. So having higher FID is a measure of both having higher quality images as well as having an image distribution that is more diverse. which is implied by the high variance values. We've also used the R precision measure to assess the accuracy of our models. So it's a measure of the correlation between the generated images and their corresponding captions. So the text and image encoders used or learned in the pre-trained DAMSM were used to extract global feature vectors of the images and their captions. And then for each image, its encoding is computed using the cosine similarity versus the encoding of the correct caption and versus the encoding of 99 mismatching captions. And if the similarity between the encoding of the correct caption with the image encoding is the top against among the 100 similarities, then it is considered in the calculation of the mean of over all the images, which is finally the R precision score. For our experiments, we have mainly followed two tracks. First is experimenting with the style component introduced earlier by having two main experiments. First is testing the StyleGAN with the DAMSM loss, and then later by testing or by introducing the style blocks to the existing AttnGAN. The second track was testing the contrastive learning, which was achieved by incorporating the contrastive loss function first into the StyleAttnGAN and later into the SSAGAN. Now more on the results of these experiments with my colleague Mahmoud.
Okay, so for our results, we first started with experimenting with StyleGAN along with DAMSM. So for DAMSM, we thought that maybe we would want the generator to focus more on edge generation and add a bit and varies the importance of the DAMSM loss. So first, when we added the whole DAMSM loss with a lambda factor of 1, we can see that the pictures were not that clear and there weren't much details in the picture. However, when we decreased it, we can see that it did improve. However, we can see that some pictures are not that good. So we moved on to the other idea that we would integrate style blocks along with the attention mechanism. And this actually produced much better images. And we can see that the attention mechanism made it, for example, when we say a white peak, it focused on the white peak, a white body, it focused on white body, and so on. Now, when we saw that it did perform well, we added a contrastive loss. So for the contrastive loss, we can see that in terms of features, it did improve. And one of the pictures that we showed in the beginning of the slides were from this experiment. However, we can see a main problem here is that each and every bird is the same shape, the same pose. So for example, all of them are sitting on a branch. None of them, for example, is swimming or flying. So when we tried SSAGAN, this is what we got. One of them is sitting on a branch. Another one is indeed swimming, and a third is flying. So we did solve the problem of having a variety of poses and birds. And when we compared against each and every experiment that we did, we can see that first we have in the literature, AttnGAN plus contrastive loss. The images itself, the details were not that good, and they did need more to work with. So when we added the style attention, the birds, for example, we can see a transition in the clarity of the images. And when we added contrastive loss, there was, at least visually for us, there was an improvement. Then when we moved to SSAGAN, after the problems that we mentioned, we saw SSAGAN on its own. It had a very good visual results, and it was good enough in the literature. When we added to it our two losses, first fake to fake, and then the combination of both of them, we can see at least a visual improvement in the features of the bird, in the feathers and the backgrounds and so on. Then when we wanted to quantify our results, we wanted to see how good are we doing compared to the literature. And to do so, we used FID and R precision. In the literature, the best accuracy that we found when we recomputed it to verify the results was LW Mani, and it achieved 9.31. And our models that we're comparing against is SSA, which had 76. Our model, which was the best one, was the combination of the fake-to-fake and fake-to-real, had a 9.12. And when we added the whole contrastive along with recaptioning, it didn't really make much of a difference, and it was more competition expensive. Therefore, in the future experiments of coco, we didn't really compare against it. And it's worth mentioning that these results so far are, this one is the best one in paper with code in terms of a metrics, and ours actually beat it.
Our results so far have been concerned with problems with single class generation, meaning that we have only been generating classes for birds only on the CAP datasets. So for the multi-class dataset, which is coco, we have chosen our two best models mainly because of the long training time. A single run on the coco dataset can take up to a month. So in order for us to better hypertune our parameters, we chose the best two models, SSAGAN with fake-to-fake loss and SSAGAN with fake-to-fake and fake-to-real losses. As you can see from the pictures, the model was indeed able to capture the general shape of the image. This is a boat, and this is a figure that somehow resembles a man snowing up, and this is some figures for something that looks like an elephant, and it's indeed walking near the river. So it captures what's in the pictures, what are the components of the image itself, and what are the relations of them relative to each other. And I would like to reference the first three images that you first saw in the model. And if you think the results does not look so well, it will look even better when compared to literature. As you can see, the first two columns are the attention plus contrastive and the SSAGAN. The first image in the top right can be a lot of things, but a clock is probably not one of them. And contrary to what we see in the SSA architecture after we added the contrastive loss, and the same trend happens with all the results. And the results will look even better when we compare it quantitatively. Our model, which is highlighted in red, beats all of our experiments, and it indeed beats the LW Mani, which was the state of the art in the COP datasets, but it is yet to beat one of the recently produced papers in the coco datasets only, which is Lafayette. But it's also worth noting that we had a 44 increase in the quality metrics from our base network with the contrastive loss only. So with better hyperparameter tuning and fine-tuning the text encoder, we hope that we can be able to beat the Lafayette paper even in the coco dataset. And it's also worth noting that for the recaptioning or the accuracy metrics, we can see that contrastive loss had a measurable increase in the accuracy itself, either in the AttnGAN base architecture itself or the SSA plus the contrastive losses on both. Finally, to summarize what we have been saying so far, first of all, we started by introducing the style-based architecture. We showed that the style-based architecture with the DAMSM loss only was not able to converge to probable results. That's why we showed the need for incorporating attention, and the attention masks that we showed earlier showed that indeed attention was able to capture the semantic meaning of the images more better, and the AttnGAN was able to produce higher results, but with lower FID metrics, as we have seen. We hypothesize this is because the lower variance in the classes itself. So we use the semantic spatial awareness attention, which produces higher quality images with higher metrics because of the high variance. And finally, we also studied the effect of the contrastive learning, and we showed how contrastive learning increases both accuracy and quality, and even did increase the quality metrics, even on the harder problem of the multi-class generation by a higher margin than a single class. And as shown here, our model and how it performs according to the state of the arts in the recent years. For the future works and the limitations that we have found, the first one, which is obviously hardware limitations. And to give you a sense, as you have seen earlier, we are working with a 3090 with 24 gigabits of RAM, and a single run on a single data set can take up to a month. And the dataset itself, it lacks the descriptive captions that we need to generalize to a higher quality and to a multi-class problem. And the size of the dataset itself is small, and it needs to be considerably larger to consider generalizing the problem. And the model capacity, we hypothesize that it needs to have a higher model capacity to help it with generalizing to the multi-class problem. Finally, for the metrics, fine-tuning the text encoder has a large effect on the R precision, as we have seen in the previous slide for the R precisions. And this should be explored as fine-tuning the text, as we can see, will improve both quality and accuracy metrics. Finally, the FID quality metrics has its limitation because you have seen the StyleAttnGAN results, and it did showed quite qualitative results, but poor quantitative results because FID metrics has limitations when data sets have lower variances. Finally, this is the timeline that we have been working on from the beginning. And at the end of the spring, we have benchmarked the results, especially with the coco datasets. We have achieved our empowerment outcome, which is writing the paper manuscript and contributing to the literature. Thank you for your time, and we are open to your questions.